Well, thank you everybody for coming out today. My name is Logan Elliott. I'm an engineer with Southwest Research Institute, and I'm really excited today to talk through our autonomous exploration of unknown areas with UAS. So a little bit about Southwest Research, if you're not familiar. We started in 1947. We have less than 20 employees at the time and less than $100,000 budget, and we have grown in 2019 to have over 2,600 employees with a gross revenue of $674 million. We're located just south of here, about an hour and a half, in San Antonio, Texas, and we do applied research and development. Our goal is to look at the fundamental research and the fundamental science coming out of universities and national laboratories and see the gap that industry is trying to fill with some of their product development and production level science. So we try to fill that gap in the middle by applying the research we're seeing at these national laboratories and make it so that the industry can pick it up and use it in their products. We cover a wide range of industries with many departments: automotive and transportation, biomedical, chemistry, defense, earth and space, energy, manufacturing, kind of cover the whole gamut of different departments. So I personally work in the Intelligent Systems Division. It's home to Ross Industrial. We do unmanned systems, robotics, active safety, perception, human performance, big data, all of these things you see. We do a variety of both ground platforms, from military vehicles to large commercial and small commercial rovers, as well as UAS. We've been working in the field since 1994 and have kind of covered a wide variety of UAS platforms, from lighter than air, VTOL, obviously UAS, manned UAS, unmanned UAS, high and low level control, advanced perception, propulsion, and all of these other things listed on this slide. So let's get into what you guys are here for, is how are we doing exploration? So we have two main platforms that we use. We'll primarily be talking about the larger Taro 650 based quadcopter with an Ouster OS0 lidar. It has an Intel NUC for its main computation and an Odroid C4, as well as a PX4 flight controller. And we've also started taking our exploration software on these larger exploratory platforms and starting to port them to smaller SWaP-constrained computing using smaller sensor horizons like that of the Modal AI Seeker. So as we sort of frame this discussion, it's like, what does our software stack look like, and how might you go about designing an architecture that makes sense for exploration? So at the lowest level, we have the PX4 flight controller, why we're all here, and it does a great job of handling all of the lower level computing that we didn't necessarily want to try and tackle. And it allows us to handle the higher level autonomy without having to spend the time and money on the low level computing. Because as a research institute, a lot of our projects are small, quick, budget IR&D focused or client focused projects where we don't necessarily have the budget to go and develop a whole new flight control software to just try and get a high level autonomy behavior out the door. So on top of the PX4 flight controller, we have a vehicle manager that handles some extra safety checks, vehicle health, performance, and kind of these safety checks that are related specifically to our software. We have a navigation manager, which handles all the things you would kind of expect from navigation: path planning, obstacle avoidance, mapping, localization. And then at the highest level, you have the perception layer, which does world modeling, exploration, object recognition, and decision making. It's designed to be platform agnostic. We've come very quickly to love the PX4 platform. Originally, we used some of the Snapdragon platforms, but the PX4, with its built-in ROS interfaces, makes it very easy to do this research and get started developing. So to do mapping and to do exploration, we need high-fidelity localization. That's incredibly important to building a map of the environment and knowing where you're at so you can go to where these frontiers might be located. For the research with the Taro 650, we use Google Cartographer as our simultaneous localization and mapping, or SLAM. And in our experience, it has less than 1/3 of a meter of drift without a priori information, and it gives you the GPS-denied capabilities that are incredibly helpful for doing this indoor exploration, allowing you to explore in tunnels, caves, buildings, and the like. And as you can see on the right, it allows you to reconstruct high-fidelity, high-resolution maps for post-processing and analysis. You have this orange structure that was located in the power plant we did testing on, and on the left you can see the post-processed structure, and it's detailed down to the railings on it and things of that nature. I know I mentioned earlier we're starting to do work on the Modal AI Seeker, and for that, it's a much more swap-constrained computing platform. So running things like Google Cartographer, first off, you don't have the sensor fidelity and range that you need to do, like with the Ouster, you have 360-degree field of view and 50 meters of range. On the Modal AI Seeker, you have about 5 meters and less than 180 degrees. So SLAM is not as viable, but you can use the built-in VIO to also have high-fidelity localization. So when we start talking about finding frontiers or just generally modeling the world, we have to have an idea of what we want to explore after or to bias our navigation towards. We'll talk about 2 different ideas that we've used for modeling the world. The first one is map processing to find unexplored regions, or what we call frontiers. So what is a frontier? That's when your data is transitioning from your known environment, where you knew where you were at, to unknown data, where you have no idea of what the world looks like. That transitory data is where your frontiers that you would like to explore to are located at. In the top right, you can see the occupancy grid that is produced by Google Cartographer. And in the bottom left, you can see our frontier layer putting out some of its frontiers that it's going to want to try and explore to. The red being either explored or blocked frontiers, and the green being unexplored frontiers. Now you might be saying, that's an occupancy grid. That's in 2D. Drones fly in 3D. So how useful is it to find frontiers in just 2D? And that's a pretty good point. We have a full 3D that doesn't leverage the occupancy grid in testing, but for the purposes of this, we're going to talk about how we did it in 2+ dimensions. So we start out in the 2-dimensional creation of the occupancy grid, finding these high levels of transitory data, and then you can extrapolate it using the voxel grid to place it in 3D to give you a 3D position. But you can also do mission-based world modeling and mission-based exploration. So in this case, as you can see in the bottom right, it was a radiation layer. The bottom right is in simulation because I think it shows the heat map better. Unfortunately, in the event we went to, we did not get great screen captures. But in the top right, you can see a little bit of the radiation layer functioning in the nuclear reactor. The long strip is a 40-meter shaft, which the drone flew up. And you can see the red banding where the radiation was peaking. We were the only people, to my knowledge, at the event that were accurately able to localize these radiation sources in the environment. So let's go back to talking about frontier exploration. Radiation is a little more straightforward because you can put a radiation sensor on there. It gives you a nice reading, and you can track based on where you've been in the environment and where you might want to go. Frontiers are a little more difficult. As I talked about, we want to find those areas in the environment where it's transitioning from unexplored to known, or yes, from unexplored to known regions, or this transitory data. Well, we did it based on doing a Hessian transform on the image to find the transitions where the image is transitioning from light to dark. As you might notice, that's on the edges of our occupancy grid. So once we found a rough idea of these frontiers, obviously not all of these are going to be good frontiers. They could be outside the bounds of the map, or in this case, you're seeing a lot of the ceiling tiling showing up in the Ouster because it could see both the ground and the ceiling. So we'll want to filter some of those out. And also, this is computationally expensive. To search the whole occupancy grid every certain amount of time takes a lot of processing power that we don't necessarily have to offer on like swap-constrained platforms. So the way we approach that is we just maintain a short list of possible frontiers. Keep 20 in memory, keep updating them, keep checking them. As that list decreases, as you explore the environment, you can start to trim down that list. Once you drop below a certain threshold, you can then search for new frontiers. And then we'll as I mentioned earlier, let the global planner move the frontiers from the 2D location to a 3D location. So as I've kind of talked about a little bit, we have a tiered path-following approach. We have a global exploratory planner, we have a local trajectory planner, and then a path-following controller beneath that. Check my time here. All right, so the global exploratory planner, its main job is to manage the incoming frontier list from the world model, use the voxel grid to find clear space for these frontiers, and then tell the frontier layer when it is finding frontiers that it is unable to position properly in the voxel grid. So we have an idea of a block list or frontiers that have been fully explored that moved from good frontiers to fully explored frontiers and frontiers that we were unable to explore for a variety of reasons. We also queue the presumed good frontiers once we have decided which ones can be placed in 3D space. and pass that into the local planner. One particular improvement we're working on in this is, as you might imagine, if you block a frontier early in exploration because you could not plan to it, your voxel grid might open up later, in which case you might want to replan to it later and try to explore that frontier. So we're maintaining a list, we're planning to maintain a list of these like frontiers that were blocked but might not actually be fully explored frontiers. So once this frontier gets passed from the global planner into the local planner, it's going to attempt to use RRT to plan from the frontier or from your location to said frontier. As you can imagine, sometimes it's not going to be able to find a plan to that, so it also has the ability to block these frontiers that we do not want to plan to. And it's going to break the waypoints up into paths, break the paths up into waypoints so that we can then pass that into the path following controller, and it allows for replanning and path disruptions, which we'll talk a little bit more later. I recognize that this is a feature that is built into PX4, at least once it's gone to our path following controller, and we could be sending just waypoints to PX4, but originally when this architecture was developed, we were using a different flight controller. So we had to write our own path following controller. So once we hit the path following controller level, as you can imagine, it's taking these converted waypoints, converting them to a set of target velocities, and then we're running obstacle detection in our proximity monitor. It's actually very similar to what James from Modal AI was talking about, where you keep track of the voxel closest to you and make sure that it's not getting any more closer. Because as it gets closer to you, you need to limit your velocities and start to slow down so you don't hit said object. If you do, in fact, stall out because the object has moved too close, you can then replan to go around the object and to avoid other obstacles that might have shown up in the environment while things were moving. Because just because you planned now to a location doesn't mean that in 30 seconds, 10 seconds, 5 seconds, however long it takes you, that that path is still going to be entirely unblocked. So all of this research accumulated in us attending the European Robotics Hackathon, or EnRicH, in Austria. It was at the AKW Zwentendorf, I hope I pronounced that correctly, nuclear power plant. This was a power plant that was commissioned in Austria several years ago. It was designed to be a fully functional nuclear power plant, and as soon as it was completed, regulation changed. Austria said, we do no longer want to use nuclear power, and so they shut down the facility. And it was never, in fact, turned on. So fortunately, they have opened this facility up graciously to companies like Southwest Research and others to be able to do exploration and missions and tests in a real-world environment. We very much could simulate what it was like to fly in a nuclear reactor without having to fly in an area that has serious radiation that's dangerous to humans. Our division does have expertise in flying in these particular environments and simulating some of the noise that comes with flying in a heavy radiation environment with cameras. But in this case, it's a safe environment to test our exploration because we're less concerned about radiation hardening for this research. So the mission, as we've kind of talked about, was to exhaustively explore and map the environment. It's also to find the radiation sources in the environment and locate them in the map. It's a GPS-denied environment, which obviously has its own challenges, where GPS would be a nice thing to be able to seed our EKF with, but because it's GPS-denied, we have to rely pretty much entirely on our SLAM and other localization methods, and it has no operator input. We had a safety pilot on site for obvious safety concerns, but during our exploratory flights, we never had any issues where the safety pilot had to take over. And it is worth noting, we had intermittent comms because of the nature of a heavy concrete environment. We had no connection to a base station. All processing was done on board. So such that operator might be monitoring it, but we do lose communication in the environment and it still flies autonomously. So none of this processing is being off-boarded or post-processed for the sake of exploration. So you can see here 2 of the high-fidelity maps we were able to reconstruct. The one on the right is the one where the radiation source was conducted. In the bottom right, there's that square where the drone flew up from this 40-meter shaft into the environment and then was able to explore. The one on the right was just a general exploratory flight that mostly stayed in 2D. The one on the right, you can see a little bit of the tracing on the left side of the image of where our safety pilot was walking around, but throughout this entire exploratory flight, it was able to fly without any manual takeover. Let's also note, as I mentioned earlier, we have that obstacle detection and preemption for when we start to deviate strongly from the path. In that 40-meter shaft, we had not anticipated it, but fortunately our software was able to handle it. There are strong wind gusts as you crossed floors. So at 40 meters, it's decently long and covered several stories and several floors. And as we crossed between them, we had strong side gusts that pushed us off our path. So then we were able to adaptively move back to the path and keep moving upwards. We've also started testing this in other environments because it's really important to get outside your lab. Turns out if you only ever test in your lab, your software doesn't ever reach peak maturity. We've tested in Cave Without a Name in Boerne, Texas, which is a much more natural environment compared to an indoor environment. This was actually a particularly interesting test. You can see at the peak of the exploration, we kind of flew up into a crevasse. And the owner of the cave was actually super excited to see a drone out there because they'd done lidar scans, they'd had climbers come out, and this was a very hard area of the cave to reach. And there, from a human's perspective, as you looked up, there was a recessed area that had strong shadows that they thought might be an offshoot into another cave. I unfortunately have to report there was in fact no offshoot. It was just a crevasse. That was not particularly exciting, but it was cool to be able to put our exploration into use in a more real-world use case. We've also taken it outdoors in the Reveille Peak Ranch in Burnett, Texas. And as you can imagine, taking SLAM outdoors is a challenge in and of itself. It was a very windy day, and SLAM is not at its happiest when the environment is moving. It's violating one of the more fundamental assumptions of SLAM that from state to state, it is not changing. In a windy day, your trees start blowing around, your features start swirling, and suddenly your localization can get very confused. Our localization did get noisy, but we were still able to navigate and explore in the environment. So just quickly talk through some of our other UAS capabilities and some of the stuff we're starting to implement or have implemented in the past. Obviously, we've done obstacle detection and avoidance, done GPS-denied environments, degraded environments, dark, noise, dripping water. We also worked primarily for landmark detection. We had a rough estimate of what the environment was going to look like, and doing swap-constrained computing to find the landmarks in the environment and navigate based on them with some a priori information. As well, in that same mission, we had to go into the location and then retro-traverse our route out. We also required the ability to fly unknown environments with unknown debris and obstacles without using SLAM. On the next slide, you'll see a picture of the entrance to the environment where sometimes it would be blocked, sometimes it would not, and we had no way of knowing and no operator input on whether that was going to be blocked. So as you can see here in the bottom right, that was the entrance to the PCV, where it could have been blocked, might not have been. We had no idea prior with heavy radiation in this particular environment. So as we kind of talk about expanding this, how is this useful in the global, more PX4 environment? So we need to expand robustness to different environments, and we need to miniaturize onto smaller platforms. That Terra 650 is great. Carrying that ouster is wonderful. 360 degrees, 50 meters, that's a great thing to be able to carry, but it's not practical because on a drone of that size, it doesn't really fit through doorways. Customers aren't interested in carrying it. So how do we miniaturize and how can we leverage other platforms for research that we don't necessarily have to develop? Things like the Modal AI platforms, Holybro, and some of these other PX4-based flight controllers and platforms, as well as higher level of autonomy. So we've been able to do frontier-based exploration, but can we do context-aware exploration? Can we do context-aware decision-making? Can an operator say, well, how about I explore that building? How do we enter that building? How do we find the entrances? How do we transition from outdoor to indoor? Can you turn off the GPS and things of that nature? As well as addressing user feedback for things like interfaces, communications, and tailoring it more to specific applications. So thank you. I recognize this is a little short on time, but I would really like to open it up to questions and start a dialogue about the research we're having here. So I'd be happy to answer any questions that you guys might have about this research and this work that we've been doing. Yes?
You talked about doing getting stuff 2D and happening. How do you deal with switching between layers or switching elements?
Right. So that's why we're trying to transition more to a true 3D frontier layer. Because when you're starting with a 2D occupancy grid, there's not a strong way of transitioning layers. You can start to do some semantic like if you know you're going to be in an urban environment, there's an understanding of when a floor probably ends, and you can maybe clear your occupancy grid or do some processing on that. But that's really not true exploration at that point. You have to seed it with some amount of information. And so we're trying to move away from using the occupancy grid for the frontiers and move to just using the voxel grid, because that has 3D awareness, and you can find a frontier that's truly in 3D. Anyone else? Sure.
You said 0.3 meters for
Mm-hmm.
what's that over?
I would have to go back and look at my notes, but I believe we've seen that in our like larger warehouses. I don't have a great metric off the top of my head on how far that area is, but it was substantial. It's not just like saying, oh yeah, it was 0.3 over 10 feet. It was a substantial amount of distance. Sure.
All doing stuff forward facing, or I guess it's all LiDAR based.
Mm-hmm.
We're just doing like 2D scans all the way through.
So it's a 3D LiDAR. So you have a voxel grid in 3D, so you have a notion of what obstacle is closest to you in 3D. When you're transitioning to like the smaller, more SWaP-constrained computing, like the modal AI platforms and some of these other platforms we've looked at, if you don't have 3D, you have to think about your path planning in a much different way. You have to point towards your waypoints more and be very context aware of, let's not move backwards, because if I move backwards, I'm moving in an unsafe direction. Obviously, there are times you have to when something enters your environment randomly, and if you keep moving forward, you'll hit them, and it's dangerous, right? So you do have to stop or move backwards, but in general, with 3D LiDAR, you can move in any direction, but as you constrain your sensor horizons, you do have to be more context aware of what direction you want to head in. You first, and then you.
Okay, I missed the first part, so I'm sorry.
Sure.
I mentioned this, but what onboard compute were you using for exploration of the nuclear?
So we used an Intel NUC, which is, it's all CPU, didn't have a GPU on there, but it's a fairly beefy processor, and it's great for the first path, but now we're trying to constrain that to use much smaller processing.
So how big was your drone then?
It was a 650 millimeter.
Okay.
Yeah, you can see it here. So fairly large platform, fairly heavy payload, because when we're starting this research, going with after a LiDAR, especially a wide field of view LiDAR with longer ranges, makes this research easier to start with. So heavier platform, more processing power, and now we're trying to take that next step of miniaturizing.
I was wondering how you were doing all that SLAM.
Right, yeah, right. Yeah, and as we move to these smaller platforms, we're kind of probably going to move away from SLAM because it's computationally expensive and stick with like VIO type solutions and work on finding like relocalization in the environment, as I think modal AI talked about earlier. And then another one in the back.
Have you tried to do this with like a stereo camera or something that's going to be noisier than your 3D LiDAR?
Yes, so we tried to get Cartographer working initially with like Intel RealSenses, and Cartographer in general is very, very finicky to get working well. We had to rewrite the Ouster LiDAR driver and some of these other like internal components to even get Cartographer to produce a good output. What we found with the RealSenses is it wasn't actually that the sensor wasn't noisy or was too noisy, is that it was too slow. It doesn't produce data at a fast enough rate that Cartographer produces a viable state estimate. You could try and like break Cartographer open to try and handle some of those and just use some of their internal like scan matching and things of that nature. But at that point, we might as well just write our own SLAM.
Do you have an idea what breeds kind of work with that, or?
Right. So the thing with the Ouster LiDAR, we had to rewrite the Ouster LiDAR driver. We found that Cartographer was particularly picky about what LiDAR you use. So like Velodyne's didn't work, and the OS1 and OS2 also don't work because the field of view is too narrow. Cartographer gets really unhappy if it doesn't see both the floor and the ceiling. So that constrains what LiDARs you can be using. And then, so that even at the 20 hertz that the Ouster can do, that was too slow for Cartographer. So when you rewrite the driver to send packets instead of waiting for the full scan, that is fast enough for Cartographer to process it. So I think once you break the scan apart, at 1024 lines, 20 hertz, it's a rate of like 20,000, but it's not necessarily a full scan. It's still a full scan as at 20 hertz. but you're sending the data faster so that cartographer can process it in smaller segments as opposed to waiting for the full scan.
Do you use the Auster rosters? They do exactly the same, they segment frame.
So we initially looked at the Ouster driver. If there's a portion of it that I'm not familiar with, there very well could be, but we wrote our own based on the Ouster driver, Ouster ROS driver, because the Ouster driver that's like published, to my knowledge, only ever sends full scans, or at least the time that we did this research and wrote this particular driver. So we rewrote it to just send the smaller packets as point clouds, because cartographer doesn't want like the packet message, it wants a ROS point cloud message.
Okay, cool. Yeah, I mentioned the packet message.
Right. Okay. Sure.
I think if it is using the real world scenario, then I may think of that sending not only the single drone, but the multiple drones. We give some more efficiencies and sharing the burden to building the map, or just increase some kind of the complexity by the
Absolutely. I think as we move forward, we do, and we have started discussing of how we would do like a cooperative mapping. The biggest challenge with that is how do you share your world model or your voxel grid, or however you want to represent that data between disparate units. So if you want to build like a 3D map in real time, I don't know about you, but my Wi-Fi is not that fast to be sharing big point clouds between several drones really quickly. So you have to rethink about how you might represent your environment for such. And you certainly could, have a shared frontier layer between the drones, because the frontier layers computationally, like just to manage that, is not that expensive. But you're not going to be able to share that voxel grid in real time. So we kind of have to think about different ways we might approach that problem. But I don't have a great answer right now of how we would tackle that. Yep.
When you're doing your experiment, when you're doing the exchange stuff, was it one single flight or over multiple?
So we personally, when we were doing it at the event, the environment wasn't big enough that we needed to do multiple scans with the battery life we had. Cartographer does give you that option from the get-go if you can put in a scan, like your last map state. There's nothing stopping our algorithms. Cartographer's not starting up in a weird state that would prevent us from doing multiple mapping runs in an environment as long as you maintain that last state out of Cartographer. Anyone else? Oh, sure.
How did it perform on like, I guess you said it was a pretty small environment, but like on like a long linear hallway versus being able to do some kind of loop closure around
Right.
a warehouse or something?
So actually, this image it's deceptively small, or the image makes this environment look deceptively small. This is a large warehouse, and I should have brought dimensions on it to give more context. But so the flight path in this environment is it's flying out to the end of the hallway. So it's not doing any loop closure until it makes that return home. And that's where our 0.3 meters of drift is coming from. So we were able to map like long stretches without loop closures. But like with any SLAM, right, you're dependent on the features in the environment. You go run it down a fully featureless hallway, good luck. And we've had problems with that in the past, where the features either repeat or there's not enough features, and you do start to lose localization. And that's a problem you have to handle when you're doing this kind of exploration. Any other questions? All right, well, I appreciate y'all coming out. I will be around if you have any questions, and thank you.